Let's jump right in. Welcome to this explainer. Today, we're diving into a highly focused tactical engineering brief. The objective here? Building a standalone mobile ad hoc network radio, a MANET, from the ground up, using very specific software-defined radio hardware. We're going to break down the exact system implementation for a Zynq-7020 paired with an AD9363, basically crafting an independent off-grid mesh node from scratch.
So here's the core engineering hurdle we're always running into. Usually you have to tether your SDR to a beefy host PC or maybe a Raspberry Pi just to handle the heavy lifting of all that networking and processing. But out in the field, in truly off-grid tactical scenarios, yeah, that's just not practical. The real challenge is going completely autonomous. We have to figure out how to take raw RF signals, convert them, and bridge them into standard IP networks entirely on board the radio itself. No external hardware allowed.
Okay, let's lay out the game plan. We're covering 5 key areas today. First, the standalone mission itself. Then, we'll decode the system stack, followed by exactly why the Zynq-7020 is our absolute go-to hardware. After that, we'll tackle that physical bridging challenge. And finally, we'll wrap up with a highly actionable 4-phase implementation roadmap.
Starting off with Part 1, the standalone MANET mission, focusing on autonomous mesh node deployment.
And rolling right into Part 2, decoding the system stack. We need to trace the journey from raw RF right up to the application layer.
To really get how this autonomous radio ticks, we've got to tear the architecture down into its 5 fundamental layers. At the very bottom, the foundation, is the RF front end. This is handled by the AD9363 chip. It's taking care of the raw analog signals, the mixing, and converting that RF into digital IQ streams. Step up one level, and you've got the FPGA logic. This programmable logic handles the high-speed digital signal processing and memory transfers. Then we hit the processor subsystem. That's an onboard dual-core ARM Cortex-A9 running embedded Linux. This right here is what entirely replaces that external Raspberry Pi. Sitting above that is our kernel and mesh networking layer, specifically leveraging batman-adv for routing alongside a tab0 interface. And finally, at the very top is the application layer. This is where your actual tactical services, things like ATAC or cursor on target, actually live and breathe.
Which brings us nicely to Section 3, the advantages of the Zynq-7020 and AD9363. This really is the optimal hardware loadout for this specific mission.
If you're building a DIY MANET radio, you've probably asked yourself, do I go with the entry-level Zynq-7010 or do I step up to the 7020? Well, the contrast is pretty stark. The 7010 is heavily constrained. It forces you to use lightweight, custom modems written as CC++ daemons on the ARM core. That's a massive bottleneck for your RF throughput because the CPU is doing all the heavy lifting. The Zynq-7020, though, it's a game changer. It lets you build full hardware modulation and demodulation directly within the FPGA logic itself, which completely offloads that burden from the CPU.
Now check out this number, 85,000. That is roughly the number of programmable logic cells you get on the Zynq-7020. To put that into perspective, it's basically a 3 times increase over the 28,000 cells you'd get on the 7010. This massive bump in FPGA DSP logic is exactly what gives you the muscle to handle complex, open-source Wi-Fi stacks and heavy-duty signal processing without the system even breaking a sweat.
And to feed all that processing power, we have a solid 1.0 gigabytes of DDR3 RAM. Why is that crucial? Well, when you're running an onboard MANET router, memory headroom is absolutely vital. You're executing an embedded Linux OS, you're running routing daemons like batman-adv, and you are managing massive packet buffers. Having that full gigabyte ensures you can juggle all of those tasks simultaneously without choking your system.
Rounding out the hardware perks, this Zynq-7020 setup comes with PL-side gigabit Ethernet. This is huge. It allows for direct packet passing between the physical hardware ports and the FPGA logic, completely bypassing any ARM CPU congestion. Plus, when you pair this with the AD963 RF transceiver, you can apply a firmware unlock that opens up full duplex coverage from 70 MHz all the way up to 6 GHz. So you're getting immense processing power and a massive frequency range, all packed into one single board.
All right, moving on to Section 4, bridging network and RF and how we solve the PHY Translation challenge.
This right here is the primary software hurdle of the whole standalone mission. Our mesh routing protocol, batman-adv, operates at layer 2, meaning it speaks in standard network packets. But that AD9063 chip, it literally only understands raw RF IQ samples. They are speaking completely different languages. So the fix is the TAP0 interface. You can think of it as a universal software translator. It's a virtual pipe living inside the Linux kernel that basically tricks the networking layer into treating our raw RF modem like a totally standard network device, successfully bridging those layer 2 Ethernet frames over to the raw IQ samples.
And here is how that bridge actually operates in practice, using a custom daemon. First up, the transmit path reads raw Ethernet frames directly from your virtual network interface at /dev/net/ton. Then, the daemon grabs those bytes, tacks on preambles and CRCs, and modulates the whole thing into IQ samples before shoving them over to the AD9363 hardware using a library called libiio. The receive path just does the exact reverse. It pulls raw IQ samples straight from the AD9363 stream, demodulates that data back into raw bytes, and writes the valid frames back into /dev/net/ton. It's brilliant. Network becomes RF, and RF becomes network totally seamlessly.
Finally, Section 5, the 4-phase implementation roadmap. We'll be using the PlutoSky R2 board and Tezuka OS to make this incredibly actionable.
Phases 1 and 2 are all about getting your environment dialed in. You're going to start by grabbing your all-in-one PlutoSky R2 board and flashing the microSD card with Tezuka firmware. If you haven't used it, Tezuka is a fantastic universal Linux build system for these Zynq chips. Once flashed, boot the board directly into embedded Linux using a UART or USB Ethernet console. From there, you just cross-compile your batman-adv and tune kernel modules, and then activate them in the kernel using a simple modprobe command.
Kicking off Phase 3, this is where we integrate the modem. Start by compiling that lightweight C or C++ packet daemon we just talked about, directly for the ARM Cortex-A9. Next, you need to initialize that virtual network interface, which you do with the command ip-tunttap add dev tap0. Once that's up, your compiled daemon goes to work. It opens /dev/net/ton and aggressively pipes all those raw frame bytes to and from the AD9363 using the libiio hardware API. Boom! You've got a working digital modem.
The fourth and final phase is orchestration. Your modem is running, sure, but now it actually needs to mesh. First, you attach your active tab0 interface to the batman-adv mesh using bat control if add tab0. Next, just bring the overarching bat0 interface up. Now, here is the absolute key for a true off-grid deployment. Take all of these commands and drop them into automated init.dod startup scripts. By doing that, the second you plug a battery into the Zynq board, it automatically boots up, creates the network pipe, launches the modem, and joins your man and mash without you having to type a single keystroke.
Total autonomy.
So you now have this incredibly high-tech standalone foundation. The Linux CPU, the FPGA logic, and the RF hardware are all perfectly synced up and running autonomously, which really just leaves one question for you. With your standalone MANET node successfully executing autonomous RF bridging, what tactical application are you going to deploy off the grid next?